We're going to start talking about the last major topic of our unit. It's called energy. Now, as we talk about energy, we're not going to talk a lot about forces, although we will address forces to some level, to some degree. The reason we put this with our dynamics unit, the reason we put it with forces, is because forces are required for energy to have energy. Forces are required to do work. And in the end, we define energy as the ability to do work. So if you need forces in order to do work, and energy is the ability to do work, the best place to put this topic of energy is in the dynamics unit. Although it's going to seem quite a bit different than the stuff that we've been doing over the last few weeks. Now, what does this mean, the ability to do work? Well, you guys know what work is, right? Like if something's happening, work is being done on something. Energy is the ability to do that. Sometimes it's actually doing it. Sometimes it's just the ability to do it. If I have a board marker in my hand and I let it go, that board marker falls to the ground. It's doing work. But if I hold that board marker up, it's not doing work, but it's the ability to do work, because all I got to do is take away my hand and it starts falling. So it's like energy is either doing something or waiting to do something. It's doing work or it's just the ability to do work. It's storing it until we're actually going to do work. Now there's two types of energies. You guys remember from Science 10 what the two types of energy are? Potential and kinetic energy. Good. Kinetic energy is energy of motion. This is when work is being done. When I drop the board marker, it's doing work. It's moving. It's got kinetic energy, the energy of motion. There's an equation that describes kinetic energy. You probably learned this in Science 10 as well. Anybody remember what it is? EK is equal to, what is it? Do you remember it? Good. We're going to say it's 1/2 mv squared. Yeah, Marcus, you said mv squared over 2. That's exactly the same thing, right? This is usually the way we write it, though, is 1/2 mv squared. M stands for mass. What units would we use for mass? Kilograms, yeah. Unless you're in chemistry, then it would be grams, but we're not. V stands for what? Speed. Good. A lot of people, when I ask this, say velocity. It's not velocity. How do you know it's not velocity? Yeah, there's no little thing on top, right? There's no vector sign on top. This is speed. Speed is a scalar. And it's going to be meters per second. Now, having said that, the magnitude of the velocity would be the same as the speed, so it wouldn't be a huge deal if you subbed in the velocity there. EK stands for the kinetic energy. You guys know the units for kinetic energy? Somebody said it? Joules, yeah. Now, mass is a scalar, speed is a scalar. We're going to multiply mass times speed squared. What do you think we're going to get for kinetic energy, vector or scalar? A car has 10,000 joules of kinetic energy to the left. Does that make any sense? No, a car has 10,000 joules of kinetic energy. It doesn't matter which way it's moving. The car has 10,000 joules of kinetic energy. So kinetic energy would be a scalar. When you multiply a scalar by another scalar, m times v, or mv squared, you get a scalar. Now the other type of energy, this is energy that's not doing anything right now. This is energy that is waiting to do something. You could say it's stored energy. What kind of energy would that be, Ella? Good. It has the potential to do something. It's stored right now. It has the potential to do work. Kinetic energy is doing work right now. Potential energy has the ability to do work, the potential to do work, but right now it's just being stored for that time when we're ready to do work. Now, potential energy, there's all kinds of different types of potential energy. We'll talk about a couple of them in Physics 20, but there's even more than those two types of potential energy. What's one type of potential energy? One type of stored energy. I gave you one already, whether you realize it or not. Yep. Yeah, something that's high up. If I have the board marker in my hand, it's stored energy right now, right? It's not doing anything. All I got to do, though, bless you, is let it go, and now it's doing something. Then it becomes kinetic energy. But as it's stored, as it just has the ability to do work, as it just is ready to go, ready to do some work, what kind of energy does it have? Potential. Specifically, we would say gravitational potential energy. We would say gravitational potential energy is the energy stored due to height, due to the height above something. We're going to spend a fair bit of time on gravitational potential energy, because that's the one type that we do deal with in Physics 20. And you're going to see that you can actually define the reference point wherever you want. We say due to a height above what? Due to a height above whatever you want. You'll see what I mean by that soon. What's another type of potential energy? Another type of stored energy. Yep. There is elastic potential energy. Good. We're going to deal with elastic potential energy in Physics 20 as well, although not for a little while. Elastic. Now, Jordan, I'm going to say elastic / spring potential energy, because when you stretch an elastic or stretch a spring, it's a really similar phenomenon, right? It boils down to the same thing. Elastic potential or spring potential. Energy. Now, these are both due to an elastic or a spring that's stretched or squished, compressed. You guys know what I mean by that? You take an elastic, you stretch it. What happens when you let it go? It flies across the room, right? If it has kinetic energy flying across the room, then it must have had potential energy when you had it stretched. That's elastic potential energy, stored energy in there. Another type is, Alex, chemical potential energy. We have chemical potential energy stored in our body. When you go to turn on your car and drive away, there's chemical potential energy stored in the gasoline of the car. Chemical potential energy stored in food. Chemical potential energy. Now, I'm going to put this in green because we're not going to deal with chemical potential energy this year. That's another course, right? That's another class. But it is a type of potential energy. You could even argue that solar could be considered a type of potential energy. It's not really doing anything right now, but it can be converted to something. Another type of energy, electrical energy. We'll deal with electrical energy quite a bit next year, but not this year. Electric energy can make an electric car go. Stored energy can be converted to kinetic energy, do work. It can make your toothbrush spin, right? Potential energy converted to kinetic energy. Nuclear, you could consider a type of potential energy. Energy that's stored in the nucleus of an atom, which we'll deal with somewhat next year in Physics 30 as well. It has the ability to do work. It's not doing anything right now, but it can. If we just release it, let it go, then it has the ability to do something. Generate electricity or make things move. All kinds of types of potential energy. We're going to focus in this unit, this year, on the two that are in blue. Specifically in this unit, we're going to focus on gravitational potential energy. The elastic / spring potential energy will come later on this year. You guys remember the equation for gravitational potential energy? EP is equal to, we've done this before as well. What is it? Good, mgh. Now, m is going to be mass, again, it's going to be measured in kilograms. G is going to be the acceleration due to gravity. I'm going to say 9.81 meters per second squared. But you understand that that can be a different number, right? You throw on the moon, then G is not 9.81, right? If you're high up on the top of a mountain, maybe it's like 9.74. We're going to make it a positive value, though. Just put it in as a positive value. And h would be the height. And that's going to be measured in meters. The height above, whatever you want. You can define it relative to whatever you want. The potential energy of this board marker right now relative to this desk as it sits on the desk is what? How much potential does it have to fall to the desk? 0. But it has potential energy relative to the floor, right? So if I define my floor as my bottom point, then h is about 0.75 meters. If I define the desk as my bottom point, then h would be 0 meters. And you can choose whatever you want, the desk or the floor, as long as you're consistent within a question. Now, potential energy. Do you think that's going to be a vector or a scalar? Yeah, it's a scalar too. All types of energy can be considered to be scalars. There are no types of energy that are vectors. There is no direction associated with energy. Energy is energy. Now, if I was to add up kinetic and potential energy, all of the energy of something, we would call that mechanical energy. The mechanical energy is the sum of all the kinetic and potential energy. And of course, mechanical energy is also going to be a scalar, because when you're adding up kinetic energy, which is a scalar, to potential energy, which is a scalar, you got to get a scalar. And of course, the units are going to be joules as well. Let's do an example here. It says a 2,000 kilogram car has a velocity of 90 kilometers per hour to the north. Calculate the kinetic energy of the car. If you're looking for kinetic energy, first of all, does north matter? No, because we're looking for the speed, not the velocity, right? But the number is the same, so that's not a big deal. Having said that, we do have to be careful with that 90 kilometers per hour because it should be in meters per second, right? Let's write down some givens here. We've got a mass of 2,000 kilograms here. We've got a speed, I don't care what direction it is, so I'm just going to write down speed of 90 kilometers per hour. We're going to convert that to meters per second by multiplying by 1,000 and dividing by 3,600. When I do that, I get 25 meters per second. And I'm looking for EK. So I'm going to say EK is equal to 1/2 of mv squared. It's 1/2 of 2,000 times 25.0 squared. Let's pull up the calculator for this. 0.5 or 1/2, same thing, times 2,000. As soon as it starts working there. There we go. 0.5 times 2,000 times 25 squared. 0.5 times 2,000 times 25 squared gives me a value of 625,000, which rounds to, how many digits should I go? 2,000 is 4 digits, 90.0 is 3. Final answer should be 3 digits. This is 3, this is my fourth. 6.25 times 10 to the 1, 2, 3, 4, 5. 6.25 times 10 to the 5 joules. One more example here for you. What's the speed of the 200-gram ball if the ball has a kinetic energy of 6.40 joules? This time we're looking for a different variable. That's not a big deal. We've got a mass of 200 grams. We've got to convert that to kilograms, 0.200 kilograms. And the kinetic energy is 6.40 joules. We're looking for the speed. We're going to write down our equation and then rearrange it. 1/2 mv squared. Looking for v. What do you got to get rid of first? We'll get rid of what's not attached, but there's nothing that's not attached here, right? So what is attached to the v? M and 1/2 m. Let's take over 1/2 m. By 1/2 m is multiplied by v squared, so we're going to take it over by, yep, so EK is equal to, or EK over 1/2 m is equal to v squared. Now, how do I get rid of the squared? Square root it. So v is equal to ek over 1/2 m square root. Now, you could have done this a little bit differently. You could have said, take the half over by multiplying by 2, because that's the same thing as dividing by 2, right? It would become 2ek divided by m equals v squared, or v would be equal to square root of 2ek over m. Exactly the same thing there. Doesn't matter which way you do it, exactly the same thing. Ek is 6.40 over 1/2 of 0.200. Okay, let's do this on the calculator. Let's say square root, bracket, 6.4 divided by, do another set of brackets for the denominator, 0.5 times 0.2, hold on, end the brackets on the bottom, and then end the brackets that went around the whole thing. Does that make sense? We get an answer here of 8. I said 8.0. What should it have been? 8.00 meters per second. Okay, the bad news is you do have some work to do here. The good news is they're pretty short questions. It's worksheet number 16. Worksheet number 16, questions 1 to 7.